So we've already had a look at what positive exponents are, but how about negative exponents? What are they? What do they mean? Well, today we're going to find out. Now I want you to consider for a moment, what does 2 raised to the power of negative 6 actually mean? Well, to investigate this, I'm actually going to have a look at some of the powers of 2 and see if I can see a pattern occurring. So let's consider something that we know. What does 2 to the power of 6 equal? Well, that's easy. That's 2 times itself 6 times, which is equal to 64. So, what about 2 to the power of 5? Well, that's 2 times itself 5 times, which is equal to 32. 2 to the power of 4? Well, that's going to be equal to 16. 2 to the power of 3 is going to be equal to 8. What about 2 to the power of 2? Well, that was equal to 4. How about 2 to the power of 1? Well, that was equal to 2. What about 2 to the power of 0? Well, we discovered that to be equal to 1. So, what's actually happening here every time I decrease my power by 1? Well, this seems to be halving or dividing by 2 with each step. In here, we decreased our power by 1 and it divided by 2. Here, decreased the power by 1, it divided by 2. Here, same deal. Decreased power by 1, divided by 2. And again, decreased it from 2 to 1, and we divided our answer by 2. When we went from 1 to 0, same thing still occurred. Decreased the power by 1, and it divided by 2. So, if we were to propose that this pattern would still continue, what would 2 to the power of minus 1 be? Well, we would take 2 to the power of 0's answer of 1 and halve it, which would mean it would equal 1 over 2. But we know that 2 is equal to 2 to the power of 1. So this is also equal to 1 over 2 to the power of 1. If we continued to 2 to the power of negative 2, well, we would have to halve a half, which would be equal to 1 over 4. But we know 4 is equal to 2 to the power of 2. So this is the same as saying 1 over 2 to the power of 2. Well, what about 2 to the power of negative 3? Well, that is going to be half of a quarter, which is going to be equal to 1 over 8. But we know that 8 is equal to 2 to the power of 3. So that's the same as saying 2 to the power of 3 here. And I'm starting to see a pattern occurring here, that every time I've got a number raised to a negative index, it's equal to 1 divided by the same base to the positive of that index. But let's have a look at 2 to the negative 4 to see if that still follows this pattern. Now a half of 1 over 8 is equal to 1 over 16. But we know that 16 is equal to 2 to the power of 4. So this is the same as saying 1 over 2 to the power of 4. And what do you know? The pattern seems to continue. So if we were to continue down and make a prediction for 2 to the power of negative 6, we're suggesting that this is equal to 1 divided by the same base, which is 2, but to the positive of that power, which is 6. So what we've seen to discover, at least for the base of 2, that if we raise 2 to a negative power, that's going to be equal to 1 divided by 2 raised to the positive of that power. But I want to consider another way of looking at it. What if we had a raised to the power of 2 and we divided by a to the power of 6? Now there are two ways that we could solve this problem. The first of which is we could apply the laws from our previous videos. Now the law that we'd be using is dividing indices with the same base. So when we divide two indices that have the same base, we keep the base, but we subtract the bottom indice from the top. So that's going to be equal to 2 subtract 6. So when we solve that, that's going to be equal to a, so keeping the same base, but raised to the negative indice of 4. So therefore, a to the second power over a to the sixth power by using our laws is equal to a to the negative fourth power. But let's take a look at what happens if we take the same problem but expand it and then simplify it. Now a squared is the same as saying a times itself twice. A to the sixth power is the same as saying a times itself 6 times. So now let's look to simplify this. We cancel this with this and it both equals 1. We cancel this with this and it both equals 1. So on the top line we've got 1 times 1, which is equal to 1. All over on the bottom line, 1 times 1, which is 1. 1 times a, which is a. Then a times itself 4 times, which is a to the fourth power. So when we expand and simplify, we've therefore found that a to the second power over a to the sixth power is equal to 1 over a to the fourth power. But if a to the second power over a to the sixth power is equal to a to the negative fourth power, but it's also equal to 1 over a to the fourth power, then what that means is a to the negative fourth power must be equal to 1 over a to the fourth power. So just like in our pattern that we looked at before, we've found the exact same relationship here. So let's summarize this. What we've found is with negative indices, a variable raised to a negative index is equal to 1 divided by the same variable raised to a positive index. So what that means is, if I've got a raised to the negative m, it's going to be equal to 1 divided by a to the m, so long as a is not equal to 0.